Well, thank you so much. And I'm really excited to be here and giving this seminar, and thanks everyone for joining and all of your respective time zones. I know it's not easy to necessarily make these kinds of meetings. So yeah, with that, I will go ahead and get started. So what I'm going to be talking today, as the title kind of alludes to, is resolving permafrost physical processes using various airborne and spaceborne geodetic techniques. And I'll be focusing just for this talk on radar and Lidar, with the caveat that there are other methods out there that can also be used. So before I go too much into the nitty-gritty, I just want to lay out a bit of a roadmap for this talk so that we can kind of all be on the same page in terms of what we'll be talking about. First, I will introduce and talk about permafrost and talk about why it's so important. This might be an area that some of you might not have as much direct experience with, depending on where in the cryosphere you kind of work with day to day. But hopefully I'll make the case that permafrost or frozen dirt is a very important and interesting component of the cryosphere. After that, I'll talk about why geodesy is such a transformative concept, or a technique, I should say, for studying permafrost and Arctic environments more broadly. And to do that, I will use two case studies to kind of illustrate that point. The first one will be looking at the impacts of wildfires on permafrost evolution. And then that second case study will be looking at Arctic coastal erosion and retreat. And then kind of one of the common threads that should hopefully crop up throughout this talk is this idea of using complementary remote sensing methods and how that can enable convergent geophysical and environmental science. So without further ado, let's talk about what permafrost is and why it's so important. So most of you have probably seen some flavor of this schematic at one point or another. This is kind of a cartoon illustration of the cryosphere and what that encompasses. So it has a lot of familiar elements like ice sheets, ice shelves, sea ice, which we'll be hearing more about later on from this seminar series, as well as things like mountain glaciers and more seasonal phenomenon like snow or lake, river, and lake ice. What we'll be focusing on is this little piece here called permafrost. So what is permafrost? Well, permafrost is defined as ground that is frozen or below 0 degrees Celsius for at least 2 or more years consecutively. So this is perennially frozen ground, hence the name permafrost, rather than things like seasonally frozen ground, which many of you who live in some of the more temperate latitudes might be familiar with in the wintertime if the ground freezes up. Since that ground thaws again in the summer, it's strictly speaking not permafrost, but seasonally frozen ground. So permafrost underlays about a quarter of the northern hemisphere. So when we consider the discrepancy in terms of landmass percentages between the northern and southern hemisphere, this amounts for a large percentage of the world's landmass. At right here is just a polar projection showing where that permafrost is. You'll note as well that there's a large component in the QT plateau here, which is often called the world's third pole. But for purposes of this talk, we'll be focusing mostly on the Arctic properly defined. And then I just want to draw your attention to these different color codes here. So we have different gradations in permafrost. At the farthest northernmost, we have what's called continuous permafrost. And this is shown schematically at the far left here. As its name suggests, continuous permafrost is spatially extensive and continuous. We have large, unbroken masses, so to speak, of permafrost. These are thick, well-developed permafrost. At the top of that is what's called the active layer, which strictly speaking is not permafrost, but it's a vital component of the permafrost and periglacial system. This is the seasonally frozen ground component. So, chemically it can be quite similar to permafrost, but this component does seasonally freeze and thaw because of its close proximity and interaction with the atmosphere. Now, as we move farther south in latitude, we transition into what's called the discontinuous permafrost zone. And this transition, you can kind of see from left to right here, this represents transition from high latitudes to low latitudes. And as we transition to the discontinuous permafrost zone, as its name would suggest, we see that that permafrost is less continuous, it's more broken up. We can have complicated patterns of unfrozen ground that are hydrologically connective. These are referred to as talics. And as you can imagine, that hydrology is much more complicated and can generate all sorts of unique phenomenon that you wouldn't see in a continuous permafrost setting, for example. Now, as you move further and further south, you have less and less permafrost as a percentage of the total volume, until eventually you get to areas where you don't have extensive permafrost and you just have a seasonal freezing and thawing regime. So that's kind of in a nutshell what permafrost is. Now, why is it important? Well, permafrost contains about 60% of the global soil carbon. And that soil carbon, if you add it all up, is about twice the amount of atmospheric carbon that's currently contained in the atmosphere. So this is a huge store of carbon within the global carbon system. Just at left here is kind of showing in a visual representation of how much of that carbon is held up within the permafrost regions. And that carbon is super important because permafrost, and specifically the active layer, which seasonally freezes and thaws, can have direct communication with the atmosphere through things like bacterial anaerobic and anaerobic respiration and decomposition, release of methane and carbon dioxide and other gases. And so this represents a large sink and source of carbon into the global carbon system. Now, that's important because the Arctic is warming at roughly 4 times the global rate. So this is the fastest changing area on the Earth's surface. And those areas where permafrost is most prevalent are experiencing unprecedented thaw of that permafrost. Now, what happens is as that permafrost thaws, more and more of that frozen relict carbon that is contained within permafrost, which you might think of as being stable, is now labile and can be introduced into the atmosphere or into surface hydrologic systems, and now is communicative in the larger carbon system. As that happens, that can then initiate positive feedback loops, which can give rise to further warming. And that's one of the reasons why the Arctic is warming so fast to begin with, because of this process called Arctic amplification. So it's really important from a carbon systems perspective to understand those rates of both input and output of carbon in permafrost systems and monitor how that's changing with time. Because this is such a large carbon store, any small changes even to that system can have large global consequences. As an addition to that, and kind of a theme for what this talk today, the magnitude and frequency of wildfires across the Arctic are also projected to increase. We've seen about a 3 times increase since 1950 in terms of wildfire extent across the Arctic. And that's expected to increase through the 21st century. And so, as you might imagine, these wildfires can in turn generate large emissions and introduce more carbon into the global carbon system. So these are kind of these unique step function events that we can kind of use to understand or take the temperature, so to speak, of the permafrost carbon system. Now, that's all well and good, but one of the issues with studying permafrost, other than the fact that it's in remote, inhospitable areas, is that it's very, very complicated. And so, we have these nice kind of cartoon images that give us a sense for what permafrost looks like. But when you actually go out on the field and take a look at it in person, it's often quite a bit more complicated than you would think. So this is just a kind of a typical vertical cross-section of characteristic permafrost on the north slope of Alaska. We can see at the top here that active layer. Again, this is the component that's seasonally freezing and thawing. And when it's thawed, this is kind of the most hydrologically active and dynamic component in periglacial landscapes. Below that, we see permafrost properly defined, which is, again, perennially frozen ground. But we can see within that, there's a large variety in terms of both expression and the amount of ground ice content. In this particular case, we can see regions of low ice content and regions of high ice content, where in some cases you can have supersaturation, so you can have larger pore volume space than what the porosity of that thawed permafrost would normally hold. And you can see even in cases of massive ground ice, like this ice wedge here. So you can imagine as you thaw out permafrost and melt that ice, that can have all sorts of complicated hydrologic effects. Right here is just another example of massive ground ice, again on the North Slope. This is me for scale and the Alaska pipeline in the background. And you can see this large block of massive ice. This is about 3 meters in height if you actually go to the base of the ice. And this feature has been melting out over about 5 years. This picture is about 4 years old now, and this feature is actually no longer there. So that gives you a sense for the time scale over which some of these changes are taking place. And then at the top right here is kind of one of the most dramatic examples of what happens during permafrost thaw. This is an example of a catastrophic coastal erosion and retreat, where you have massive blocks of frozen ground that slough off as the permafrost thaws. And we'll come back and look at some of examples of this later on in my talk. So because permafrost is so complicated, that can make it hard to study, particularly if you're interested in kind of regional to global scale assessments of permafrost systems. And that is why remote sensing is kind of one of the premier tools to study permafrost. And specifically, today I'll be talking mostly about interferometric synthetic aperture radar, which is a technique that I work with a lot. So what is InSAR? So InSAR is an active source radar remote sensing technique. For those in the cryosphere or in glaciological communities, you've probably seen or worked with some products derived from InSAR. So things like ice velocity maps are all based on InSAR observations. The way InSAR works is you have, if you can generate multiple spatially co-registered radar images over an area, you can compare the difference in phase at a pixel by pixel basis between those images. And that change in phase is directly proportional to a change in the line of sight distance between the ground surface and the platform. And so if you know the orbital position, you can back out how that surface of the ground has deformed or moved between your image acquisitions. Now, this is a really powerful technique because it allows you to measure with centimetric accuracy and in some cases millimetric precision ground deformation at fine spatial resolution and broad extent. At the bottom here is kind of one of the canonical images used in the InSAR community. This is from the 1993 Landers earthquake in California. And this was kind of the event that put InSAR on the map, so to speak, in terms of its potential as a geophysical technique. Now, to briefly talk about what the InSAR signal is and how we make sense of it, we can start again with a similar image here at left. So when we generate an interferogram, we have something that looks broadly like this, but there are all sorts of components that make up that signal. And in most cases, we're not interested in all of them. Now, depending on who you ask, you know, one scientist's signal is another scientist's noise. So your interest might span this range of phenomenon. But generally speaking, this signal is composed of what we call a true deformational signal. So in the case of a geodetic signal or something like a volcano, that's maybe its magma chamber is expanding and the ground is rising as a result, that is our signal of interest. But superimposed on top of that are things like signal decorrelation, which is an error source that we're usually not interested in. There's a topographic component here. And then we can also have error terms that are due to the atmosphere or things like thermal noise. Now, usually we're interested in this deformation signal. And so the question often becomes, how do we get rid of or minimize these other error terms? Now, for many applications, that's not too much of an issue. Like, for example, in the case of the Landers earthquake, where you can have centimetric to metric scale deformation signals, that's going to swamp out any other error term that you have. And so if you look at kind of the natural history of InSAR and its applications, the community has kind of had this bias towards large displacements, which makes sense because they're easy to see and oftentimes they're the most interesting signals geophysically. So InSAR has been used to look at things like volcano deformation, aquifer subsidence due to groundwater pumping, ice sheet motion, and earthquakes. But again, these are large signals. And so if you're interested in small signals like what we'll be talking about today with permafrost, oftentimes you're in a regime where those error terms are comparable to or even larger than your signal of interest, which can often necessitate sorts of clever signal processing or time series analysis approaches to parse out those signals of interest. So to go to the case of permafrost, why would we use InSAR for permafrost? As I've said, InSAR has both fine spatial and repeat temporal sampling. So this is always attractive for any kind of an image acquisition. Another great thing is that in general, it's broadly insensitive to atmospheric conditions. And I say that kind of loosely because if you recall just 2 slides ago, I mentioned the atmosphere as an error source. Now, it is an error source, but oftentimes we can mitigate for this. And I'm not going to go too much into how that is done for the purposes of time, but just suffice it to say that often these errors can be accounted for. But what really makes InSAR so great, and actually before I should say that, one of the reasons why radar in general is so attractive in the Arctic is because we have, in some cases, very limited cloud cover. And so if you have cloud cover over most of the year, if you're looking at, say, Landsat images, that might give you only a handful of images over your time period of interest. So with radar, we can see through those clouds and have a more unbroken record. Now, InSAR is great in this case because we can directly measure the seasonal freezing and thawing of the active layer, which oftentimes is a signal that we're interested in if we're interested in the component of the permafrost system that is the most hydrologically and geochemically dynamic. How are we sensitive to that seasonal freezing and thawing? Well, how we're sensitive to is, let's just jump to that next slide, actually. So if you remember from, say, high school chemistry, one of the things that makes water so unique is that it's kind of counter to every other compound in terms of its density. So as water freezes and goes from liquid to solid, its density actually decreases. And that's why, your ice cubes float, for example. And that property, when that manifests in frozen ground ice, when we have seasonal thawing of permafrost or of the active layer, that pore space that was taken up by frozen ice is now a smaller volume when it undergoes a phase change into liquid water. And as a result, for any given amount of thaw of permafrost that we experience, the ground will subside as a result, as the amount of water takes up less and less volume. So you can imagine that at the onset of thaw conditions in early spring, when your active layer starts to thaw out, for any incremental depth or any incremental thawing depth, you'll have a corresponding subsidence of the ground's surface. And as your thaw season progresses, your ground will gradually thaw out and subside. Once you get to autumn and you have refreeze conditions, your active layer will freeze back up and your ground will uplift as a result. And you can imagine over a single season, you have something that looks broadly like a sawtooth pattern, where this would represent thaw, 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 and then refreeze in autumn. Now you can imagine if you have a time series over many subsequent years, you can develop like an interannual deformation signal where you might have a seasonal component here superimposed on a long-term trend, which might have to do with irreversible changes in permafrost thaw. So in general, we can kind of consider these two harmonics, if you will, a seasonal harmonic, which we can characterize by the amplitude of that seasonal subsidence, which we call E here, and then an interannual long-term trend, which we can, for simplicity, often model as just a linear trend with a slope R. Now, borrowing from the time series community with InSAR, we can develop a system of linear equations that can relate all of our interferometric observables, in this case represented by this vector of delta phi's. And then we can build a system of linear equations that relate our interferometric observables to these two components, the linear trend and then the seasonal amplitude. And then we can relate those by respectively, the changes in time in terms of our two interferometric observations, and then this empirical scaling that has to do with the accumulated degree days of thaw. And this just comes out from fundamental physics. If you look at the way thaw fronts progress, they have kind of this square root of time dependence. So if we can form this system of linear equations, we can invert it and then solve for these two deformation signals that we're interested in. And this kind of a technique, which was first proposed by Lin Lu in 2012, has now been used more and more to study different aspects of the permafrost environment. I just, for flavor, show one example here. So this is a time series generated over the north slope of Alaska. If you look at this seasonal subsidence, which is that E term from our previous slide, this gives you a sense for how much the ground is thawing and subsiding over a single thaw season. So our warm colors indicate large thaw, cool colors indicate little to no thaw. And at the bottom here is just the root mean square error, where if we can subtract our modeled observables from our time series. What you notice is that, we have these system of rivers which experience, as you would expect, no thaw, and then you have a fair amount of heterogeneity across the tundra surface. In particular, you'll notice this large yellow patch here, which actually corresponds to the 2007 Anaktuvik River fire. So what we're seeing is that about 10 years after the fire, we still have pronounced and elevated seasonal subsidence with respect to the unburned tundra around it. And then right here, we can just kind of see how that seasonal subsidence behaves in kind of this square root of time behavior. So that's one example of how we can apply this kind of time series analysis to study permafrost systems. And we've seen just anecdotally that wildfires seem to have this effect where they increase seasonal subsidence after they burn. We're going to talk about that in a little bit more detail now, looking at a specific case study in the Yukon-Kuskokwim Delta in Southwest Alaska. So that's shown right here by the outlines of this red box. If you remember to one of the first few slides, this is now in the discontinuous permafrost zone. So less extensive permafrost, like in the previous slide, more complicated hydrologic systems. You have discontinuities, you have areas of perennially unfrozen and frozen ground nearby each other. And this area was chosen very deliberately, actually, because if you notice here, it's experienced a large number of wildfires over the last 50 or so years. So in orange are the spatial extent of various wildfires over this study site, with the years of the fires noted beside them. So you'll notice that we have fires from 1971 all the way to, in this example, 2007. And then actually in 2016, there was a massive complex of fires that basically burned up the entire extent of this study site here. So this is a very dynamic environment. For the purposes of this talk, we won't be talking about those most recent fires because we're looking at ALOS imagery, which only goes to 2011. So we're only concerned with these fires that span or precede our InSAR time record. But because we have this very nice temporal sampling of fires in a very small spatial area, this gives us the natural laboratory to do what's called a space for time analysis. So assuming each of these wildfires behaves more or less similarly, and that the wildfire permafrost interactions from different events are comparable, we can look at the geodetic signatures associated with these different fires as a function of time since burn, and try and extrapolate what that temporal evolution of permafrost that's been affected by wildfire might look like. Now to do that, we're gonna look at InSAR and do the time series analysis that I've talked about previously, looking at those seasonal and long-term components. And then we're also, in this particular case, we did some in situ field measurements for calibration and validation, which includes things like ground penetrating radar measurements of the active layer thickness, and probing measurements, which basically entails taking a metal rod, sticking it into the ground until it contacts that permafrost table and it can't go in any deeper, and then measuring how deep that active layer is. So cutting right to the chase, if we look at these results, looking first now at just our estimates of the seasonal subsidence, which is that E term or that seasonal amplitude, we can see that over our study area, we can resolve some differences in seasonal subsidence. We have values on the order of 0 to 4 centimeters per year, which is pretty typical for discontinuous permafrost environments. And using some simple soil physical models, we can actually convert that seasonal subsidence into an estimate of what the active layer thickness is. So again, that active layer thickness is the maximum extent of the thawed layer over a given seasonal cycle. And it's a little bit hard to see here, but the outlines of these fires are in gray here. And you'll notice that there are a few fires like this 2007 fire and this 2006 fire that seem to have elevated seasonal subsidence values. But a lot of the older fires don't really have an obvious signature. They look more or less comparable to their surroundings. If we compare our results to in situ GPR measurements, like here at right, we can see that in general, the comparisons agree quite well in areas where subsequent burning did not occur, such as here. But in areas that were affected by the 2015 and 16 fires, such as more close to this marginal lake here, we basically have no match between the results. And that's because this most recent fire has further modulated that system. And so comparing it in situ contemporary measurements from 2016 to remotely sensed measurements from 2011 are no longer comparable. But what this supposedly should be convincing you of is that in areas where we don't have further modification by fire, InSAR seems to be doing a pretty good job of estimating the active layer thickness. Now, if we look at the interannual trends, which are those long-term linear trends, now we're seeing a little bit more compelling signature. So at right here is that subsidence trend, that slope of the linear model. And we now notice a much stronger spatiotemporal correlation between subsidence trend and fire scar. Particularly now, if we look at these fire scars and we look at the time since burn. So in the most recent fires, like this 2007 and 2006 fire, we see elevated trends at about 3 centimeters per year. So this means that the active layer is thawing out approximately an additional 3 centimeters additionally per year. So that active layer is deepening, in other words. In more middle term fires, such as the 1972 fire or the 2002 fire, we see lower trends or even trends that are more or less around 0. And then in some of the oldest fires, like this 1971 fire here, we actually see negative trends. In other words, recovery. Our active layer is thawing out less and less in subsequent years. Now, if we go ahead and plot those values as a function of time since burn, we notice this exponential relationship, where again, this cluster is recent fires from 2006 to 7, intermediate fires, and then older fires. We can fit an exponential model to this, and then if we integrate that exponential model to develop, functionally a proxy for expected surface deformation as a function of time since burn, we get this integral of an exponential effect. And what this basically tells us is that from time since burn, we can expect an increase in thaw or a deepening of the active layer, and then eventually a recovery as that behavior bottoms out more or less, and then has a much slower, longer tail recovery. Now, because we've separated both the seasonal component and the interannual component, we can actually further discriminate between effects that modulate the active layer, which is that seasonally freezing and thawing component, as well as effects that influence the permafrost, which is that perennially frozen component. And so what that's shown here, where in red we have the seasonal component, and in blue we have the forward model of the long-term permafrost changes. And so what that is showing us is that there's appears to be two fundamental recurrence intervals, if you will, in terms of how permafrost and periglaciated environments respond to wildfire stressors. When looking at the seasonal active layer, or the shallowmost part, we see that over a process of about 20 years or so, we have a deepening of the active layer, followed by a recovery, and that by about 25 years or so, the active layer seems to recover to its pre-fire conditions. But if we look at the geodetic signatures associated with the permafrost at depth, we see that recovery takes much longer, and that by 25 years, we've just about stabilized, and the permafrost is no longer thinning. And then there's a much more gradual recovery that takes almost 70 years to occur. So if we're looking at permafrost at depth, what we're seeing is that wildfire can modulate that on decadal timescales. Now, that recovery also gives us a sense conceptually for what this recovery process looks like, which is shown right here in another cartoon schematic. The reason we have this modular recovery rate is if you imagine, say, a one-dimensional soil transect of permafrost, where we have permafrost in blue, active layer in gray, and then the insulating organic layer of mosses, lichens, and dead organic matter, that wildfire is going to burn off some component of this thermally insulative layer, which then perturbs our system from any sort of thermal equilibrium that it might have been in. What this means then is in subsequent seasons, the thermal insulation is all out of whack, so to use a technical term, and we can expect deeper thaw in subsequent seasons and thinning of the permafrost at depth. Now, slowly, as you reaccumulate that organic layer, you have more and more thermal insulation as you have further organic matter dying and accumulating, and so that effect will lessen with time until eventually it starts to recover. And so that, in effect, is what we're imaging here and then forward modeling with our observations. Now, just to make sure that, just to keep me honest, we can actually now look at some ecological observations and see if they're telling a similar story. So this is work that was led by J.J. Frost up in Alaska, looking again at the same complex of fires in the area. Shown here. We have, of course, have used a different color scale just to make comparisons a little bit more difficult, but hopefully some of these shape files look familiar. These large red ones are those 2016 fires that I was talking about. So again, my older study was not concerned with these, but more so with these older fires behind them. But if you go ahead and look at some plant functional type maps that JJ derived from hyperspectral imagery, he has a classifier that can look at the percentage of different vegetation components. So say the percentage of shrub cover, lichen cover, and bryophyte cover. And just as we did, we can do a space for time swap and see how that ecological cover changes as a function of time since burn. Right here is just giving you a visual sense for how dynamic these surfaces are from an ecological perspective. We can see that immediately post-fire, we have the loss of most of the lichen in the area. Some sphagnum might still remain. And then in recovery, we have gradual reaccumulation. There's a point where we have a large amount of vascular plant recovery before mosses and lichens, and then shrubs dominate until about 45 years post-fire, we're kind of in this pre-tundra condition again. And if we look at those plots as a function of years since fire, we see more or less the same exact signal that we can get with InSAR, which tells us that we have this integral of an exponential effect on mean thaw depth, which we can think of as a proxy for the seasonal amplitude. We see it increases in the first 5 to 10 years post-fire, but then by 32 years post-fire, we're more or less trending towards that unburned state. And then we also see that surface organic thickness takes about 10 to 20 years to recover to its unburned state, which is more or less consistent with what we see in the seasonal component. And then we can further see that a Simpson's diversity score, which is telling you how diverse that ecosystem is, takes, again, several decades to recover. So what this is telling us is that these ecological observations that are both remotely sensed and from field measurements are consistent with our InSAR observations. And so we really have some confidence that these results are telling us something fundamental about that wildfire permafrost interaction system and the timescales over which that process plays out. So that's kind of the first case study I wanted to talk about. I'm now going to transition to another case study. This one now uses laser altimetry or Lidar. So this is to give a flavor for another form of geodesy that we can use to study permafrost systems. So what is LIDAR? For the purposes of this talk, we'll just be talking about observations from ICESat-2, which many in this room may be familiar with, but this is a NASA mission that was launched in 2017 or 18. And it's a laser altimeter, and it has 6 beams. It's a photon counting laser altimeter, I should say. So what this lets us do is actually build up 3-dimensional photon clouds and photon densities from the surface for things like looking at vegetation canopies. So this really is at the cutting edge of laser altimetry in terms of providing estimates of topography and topographic change. Now we can get topographic change because this is in a near polar orbit, so we can get temporal repeats about every 91 days or so. So every 91 days, the satellite will return in its orbit over an area and collect a repeat topographic transect. Now, this cartoon just gives you a sense for what those observables look like. We have 6 beams in pairs of 2. So we have one pair that's directly at the nadir point of the satellite, and then 2 pairs that point off in either direction. And what this gives you is a broad spatial sampling over and along the flight direction of the satellite. These pairs are in strong and weak beam pairs. The reason for that has to do with difference in quality over, say, land surfaces versus the ocean. So depending on what your target of interest is, you might be more interested in the weak pair versus the strong pair. For our purposes, we're mostly interested in those strong pairs because they give you better retrievals over land surfaces. We'll also just be talking about 2 products from ICESat-2, so ATL-03 and ATL-06. Broadly speaking, we can think of these as photon clouds or surface slopes. So I mentioned that this is a photon counting altimeter. The way that works is at each pulse, the satellite sends out something like 3 trillion photons. They get sent down to the surface, they interact with the surface in some manner, and then are scattered back. And then the receptor on the satellite will receive on the order of 12 photons. So the fact that the satellite can really measure and count those individual photons is truly remarkable. And what it does is it can count out and generate a 3-dimensional distribution, so to speak, of where those photons occur. And so if you imagine sending out transmitted photons more or less in a beam like this, depending on the surface they interact with, you're going to get different responses. So if you interact with a flat surface, you would expect all the photons to bounce back in more or less the same orientation that they were transmitted. If you have a rough surface, that's going to introduce complications because you have photons that, say, hit on this point or this point returning before the photons that hit at the troughs of this surface. So that in general, that's going to cause a broadening of the distribution and less photons returning, as photons will get scattered off in angles away from nadir. Similarly, if you have a sloped surface, that can introduce kind of a slope to the photons, as these photons here are going to be returned earlier than photons down here. So if we look at ATL-03 products, that will give us a sense for what that distribution and density of photons is, from which we can often back out characteristics of the surface. And then if we look at ATL-06, this is just kind of a higher derived product where if we look at the actual photon distributions, we can then fit, for example, a surface slope to different windows and transects. And so this is usually done at 40 meter bins. So you can think of these as basically giving you estimates of surface slopes at 40 meter step sizes. Now, the particular case that we're going to use to look at using LIDAR for Arctic and permafrost environments is this phenomenon of Arctic coastal erosion and retreat. So if you remember that picture that I had at the beginning of my talk of that massive block of permafrost that had rotated off from the coast and was now sitting in the ocean, that is just one component of how Arctic coasts both erode and retreat. This cartoon schematic gives you a sense for other phenomenon and processes that are part of this system. But the reason this is such an important component of how the Arctic is changing is that these coastal environments often contain some of the largest densities of carbon. And that carbon, as you can imagine, can enter the ocean, where it can have all sorts of impacts on local ecosystems, and then also make its way to different sources and sinks in the global carbon cycle. The Arctic is also unique in that it's experiencing some of the highest rates of coastal erosion and retreat anywhere on the Earth. This can be rates as large as tens of meters per year in any individual area. So you can imagine with that rotating block, if you have several such events, that can dramatically change the coast over a single thaw season. But we also have more slower migration of the coast due to other physical properties. So again, this is a very dynamic component of the Arctic, and really an area that demands to be understood better. This gives you a sense for how Arctic coastal erosion and retreat works in the kind of more conventional system, where you don't have these single catastrophic events, but fundamentally the two forcings that give rise to coastal erosion are thermodenudation and thermoabrasion. So thermodenudation we can think of as an atmospheric forcing phenomenon. This is similar to what we were talking about in the previous case study, where we have seasonal freezing and thawing of the active layer and melting of pore-bound ice, which gives rise to thaw of the permafrost. When that permafrost thaws, it's much less cohesive than it was in its frozen form. So that can give rise to all sorts of phenomenon like solifluction or sloughing or subsiding of the ground. And in coastal environments where you have slopes, that causes the ground to erode away, basically. We can also have thermoabrasion or oceanic forcing, where you can imagine that warm ocean water will actually cause permafrost at the base to thaw out. And then if you have a lack of cohesion at the base of your coastal bluff, that can cause all sorts of structural issues and give rise to things like those catastrophic failures that we saw earlier. So these are kind of the two more or less most important forcings that give rise to Arctic coastal erosion and retreat. And they're controlled to first order by atmospheric conditions. More or less air temperatures have to be greater than 0 for thermodenudation to be a significant force. And then we need sea ice free conditions. So basically, if there's no sea ice in the area to insulate the coast from wave action, we can then have wave action come in and modulate the surface. So these are the fundamental forces that we're thinking about. And this is just, again, to give you a sense for how this manifests in really dramatic ways. At right is that image we saw first, and then at left is an example of coastal bluff collapse. In this case, this was an indigenous community in Alaska that had to be abandoned due to these coastal retreats. And just to be kind of timely, some of you may have seen just last week, there was a storm surge in Western Alaska. This is a GNSS signal from Christine Larson showing wave heights on the order of 4 meters higher than their normal comparable wave heights. So this, and this single event caused a huge amount of coastal erosion, retreat, and flooding all across Western Alaska in the area from Nome to Emmenak. So this is just one kind of concrete example of how, in addition to, say, seasonal forcings, we can have these episodic forcings that are oftentimes modulated and further exacerbated by warming air temperatures that can have step change, immediate and remarkable effects. So this is just to give you a sense that these phenomena are very much happening in real time and really as we speak. So to go now to looking at some preliminary results of this work, I want to mention that this is work that's being led and really championed by Marnie Bryant, who's a phenomenal grad student at UCSD. I think she might be on the telecon here as well. So if you have any questions on this, Marnie can probably answer them better than I can. So I just want to mention that this is work that she's really been leading. And what I'm showing here is some example of Marnie's work using ISAT-2 topographic profiles in conjunction with high-resolution optical and hyperspectral imagery from CubeSats from the Planet constellation. And what she's doing here is she's combining that three-dimensional topographic information from ISAT transects, which are more or less perpendicular to the coast, in conjunction with coastline positions that are derived from images from high-resolution optical images. And what you can see here is that over just 2 years or so, we're capturing a really remarkable retreat rate on the order of about 60 meters or so. And if we look at the three-dimensional topographic profiles, we can again see that coastward migration of the coastal position, but also complicated changes in the near coastal topography as we go from 2019 all the way to 2021. And what this is showing us is that ISAT is really giving us this fundamental three-dimensional insight into the geomorphology of this system, which you can't readily get with more conventional two-dimensional imaging systems like optical, hyperspectral, or radar. We can now take a look at what, so that previous transect was showing you examples from ATL06. We can also look at photon clouds themselves here. At the top are, again, those planet images. And this is demonstrating how Marnie's developed a classifier based on NDVI to discriminate between the land and the ocean from which those coastal positions can be derived. So this is an image from early 2019, and then 2 images from early to mid 2021 with the 2019 image superimposed with this blue line here. And what this is showing is that we're really resolving on the seasonal scale, coastal retreat rates, and that ISAT-2 is giving us a fundamental look into the geomorphology, which we can't get just from those images. In this particular case, we can see from this second scene in July of 2021, we've got what seems to be evidence for near surface ponding. This area here, the photons are more or less collapsed around a single elevation, which is often consistent with interaction with standing water. So this seems to be evidence that we have actual ponding of water near the surface, which then could give rise to thermal abrasional erosive processes as that water thaws out the permafrost and then causes slope instability. Now, finally, we can also throw in some InSAR observations to really give us a complementary view of how this coastal system is evolving. So again, we've got our optical images showing that coastal retreat rate. We've got our ISAT transects showing the coastward migration of bluff positions. So in this case, we can see that from 2019 through 2020 into 2021, we've had a migration of about 60 meters for this particular transect here. But then in these 2 other transects, which are just a few hundred or a few kilometers, down the road, so to speak, we can see situations where we have less erosion. We have complicated hydrologic systems going again, that pooling and thermal abrasive phenomenon. And then just farther down here, where we have a breached thermokarst lake, there doesn't seem to be any coastal retreat here. So this is really shedding insights into how complicated this geomorphological process is and how it plays out in time. And that complexity has to do with things like ground ice content, which you can't infer a priori from space because by definition it's in the ground and you can't see it. So ISAT is really giving us this fundamental view into permafrost systems that you would otherwise need to get from, say, dedicated in situ geophysical measurements. Lastly, just by throwing in InSAR here and getting a sense for what those deformational geodetic signatures look like, we can see that we're resolving all sorts of complexity associated with, for example, breached thermokarst lakes, where we have increased thawing as those banks erode away. We have increased subsidence in this river delta here, where we have sediments coming in and depositing on the delta. And we can see all sorts of changes that further enrich our understanding of how this Arctic coastal retreat process works. So I just want to note again that this is still a work in progress that Marnie is hoping to publish in the coming year or so, but I'm really excited at least by it because I think it really sheds a valuable light into how Arctic coasts operate and evolve in time. So with that, I'd like to more or less tie up because we're approaching the hour, but hopefully I've convinced you that permafrost is both interesting and important from a cryospheric and a global carbon perspective. Hopefully you've seen now how certain geodetic techniques can be used to study permafrost, and in my opinion are really transformative because they're giving us process level understanding that we would otherwise need to acquire with costly in situ surveys. And kind of the thread that runs through my research interests and those of folks like Marnie is kind of using complementary remote sensing methods that enable these convergent studies. So with that, I will leave it there for any questions that anyone in the audience might have.
Fantastic. Thank you very much indeed.
Thanks.
So the way that we've traditionally done questions is that people give a quick indication on the chat and then we'll get people to unmute themselves. Paco, you have a question. You want to unmute yourself and ask.
Yes, hello, nice talk.
Thank you.
I have a couple of questions or curiosities. First one, you have been talking about this regarding the permafrost and the wildfires. You have been talking about the Alaska case in southern Alaska. And I wonder whether your results, for instance, the results regarding the recovery times for the active layer thickness or the permafrost thickness following the wildfires could be extrapolated to other regions such as Siberia, which are rich in both permafrost and wildfires? Or is there any study similar to yours done in Siberia?
Yes, that's a fantastic question. So there have been a few studies since that paper was published in 2019 that have looked in eastern Siberia and using similar methods. To your first question of whether or not these results are generalizable, I would say it's very much an open question that remains to be seen. And so that's something that I'm actively working on now, is looking at areas in Siberia where we have large densities of fire clusters across time. As many of you are probably aware, the last 3 years have been landmark years for wildfires in Siberia. So this is really, an important topic for understanding Siberian science. So yes, it remains to be seen. I would say it's generalizable to an extent in that we expect comparable decadal recovery rates. But in certain areas that are more marginal, say in sporadic or isolated permafrost environments, recovery may not actually happen. It's possible where if this fire is so extreme, you can knock the system totally out of thermal equilibrium, and you effectively have irreversible thaw of permafrost. So understanding, what regime a lot of Siberia is in is still very much a work in progress that hopefully we'll have a better understanding of in the coming years.
Okay, and the second thing was a pure curiosity about you were showing the first of the figures that you were showing about the retreat rates in the Arctic coast. I think I noticed that in year 2019 to 20, the retreat rate was much higher than as compared to the other two later years. Is there a reason for that, or what happened in that year?
That's a great question. So I'm not sure, but what this really highlights is that oftentimes we kind of like to think about linear and nice continuous retreats because it's easier. Those assumptions let us do all sorts of temporal averaging. But what this fundamentally tells us is that those retreats are not constant with time. And so really, as we kind of transition into this era of, having a luxury of orbiting satellite imaging platforms, we can start resolving these non-linearities with time. In terms of the actual process that gave rise to that apparent decrease in erosion. I'm not sure, but it's definitely an area that we should look into.
Okay, thank you.
Thank you.
Marnie Brent, do you want to unmute yourself and ask a question, or?
Sure, yeah, just to elaborate. Yeah, I've been looking at or trying to find imagery over the 2019 season to figure out why there's been so much thaw. And the short answer is there's pretty much no satellite imagery because there's so much cloud cover. So not really an explored hypothesis yet, but yeah, I think there may have been a lot of storms that year. And that could drive a lot of episodic erosion events like Roger mentioned earlier. But yeah, still a bit more work that needs to be done there.
Okay,
Great.
thank you, Marnie.
Sorry, I should have been checking slides and providing an answer rather than asking a question.
No worries.
So does anyone else have questions? So Andre, would you like to unmute yourself, or is it?
Well, I can.
Yeah, excellent.
How separate the vertical movement, subsidence, from downslope movement, like a sort of fluxion or something like that?
That's a great question.
In InSAR, well, and the second maybe also, well, later.
Okay, yeah, so to answer your first question, it's hard, right? And so for the first case, we kind of had the luxury that we're working in an area that's incredibly flat, less than 1/10 of a degree of topographic relief over, say, 100 kilometers. So in that kind of an environment, it's trivial to make that geometric projection from line of sight to vertical. But for cases like this coastal application where you have significant slopes, you can't really make that assumption. So I was kind of a little clever in that the slides I showed you, I had them in line of sight projection rather than vertical, because I didn't want to make too large of claims that we were resolving vertical subsidence in that particular case, because yes, in this particular example, what we're fundamentally sensing is the projection from line of sight onto whatever the local tangent of the slope is. And so in Arctic coastal environments, that's very much a non-trivial thing. Now, one way you can get around that is by combining ascending and descending track observations. So that gives you a look angle from two different directions. And with that, you now have two vector observations, so you can actually fundamentally back out projections into east, north, and up. That's a little complicated in the sense that we're in near polar orbits, so our sensitivity in the north and south is particularly weak. But when InSAR launches in 2024, that's going to give us a much better sensitivity to actually fundamentally break out that three-dimensional vector orientation. But yeah, so sorry, what was your second question?
Oh, second question. You know, there is changes of the condition on the surface. There is some snow cover or just vegetation in springtime and summertime. So what is the effect on the InSAR signal? I don't know, on penetration or something like that of this changes of the condition?
Yeah, that's a great question. So all of those things, snow cover, changes in, say, soil moisture or vegetation, can all cause interferometric decorrelation, which if you remember back to one of my first slides, that's a significant error source. And so in practice, that limits the number of usable interferogram pairs that you can use for time series analysis. What we've noticed is that, so the results that I presented in the first half of the talk are from ALOS, which is L-band. So at lower frequencies and larger wavelengths, you're less sensitive to that decorrelation. And we have quite good interferometric coherence, even across interannual pairs with wintertime acquisitions. But at C-band with Sentinel, decorrelation is pretty severe. And so you're often restricted to using interferometric pairs with temporal baselines of about 48 days or less. But to answer your question more generally, it's very much something that has to be taken explicitly into account. And if you were to say, just take all the interferograms you have and run them through like a time series inversion, you would want to interpret those results with a large grain of salt, because you're going to have a lot of errors in there. I didn't talk about it here, but there are all sorts of kind of clever error mitigation techniques that you can go into, making use of things like interferometric phase non-closure to kind of empirically remove those error terms. And that's something that I've worked a bit on in the past, but yeah, I didn't have time to go into that for this talk, but I'd be happy to chat more if you were interested.
Thank you. Very interesting.
Are there any further questions for Roger? If not, would you possibly be able to put next week's talk title up for us, Roger?
And I'm going to blow past a few slides that I did not have time to talk about. But yes, so that should right here.
Brilliant. Thank you ever so much. So next week we have 3 early career scientist talks from Sonia Rall, Shastak Shukla and Peter Washam, and the titles are on the screen there. So hope to see people back for next week's seminar. So thank you very much indeed again, Roger, and yeah, great start to the seminar series. So thank you very much.
Well, thank you for having me, and thanks everyone for attending.
Excellent. Right. See everyone soon.
Thanks, bye.